Hello, and welcome to the Military Standard 1553 Differential Data Bus Testing Suite. In this video, we'll be taking an in-depth look at what it took to create this project and the obstacles we overcame along the way. Introducing the team, starting from the left, is myself, Jacob Vanderveen. In the middle is Joshua Johnston, our point of contact. On the right is our secretary, Nico Fernandez. And then our other two team members were Andrew Townley and Corey Sutter. The sponsor of this project was GE Aviation, and our faculty advisors were Dr. Carl Bacora and Dr. Brian Krug. Our project scope was a little hard to define in the beginning, but eventually we got to an understanding that our project was to create an easy-to-use, portable, and effective testing suite to replace the current methods of outsourcing the testing that GE currently does. This method promoted very little debugging potential and long lead times, and they couldn't control it very well. So what we had to do to replicate this testing suite was create a GUI, or graphics user interface, that allows test selection, bus selection, channel selection, shows the equipment used for the test, and customer information. Then we had to create a noise generator that outputs white Gaussian noise over a range of frequencies normally distributed from 1 kHz to 4 MHz. Some of our goals in this were seamless communication between lower level software and upstream controlling software. Communication between software and measuring equipment, including capturing relevant scope captures upon test failure, was also a big goal for us. Streamlining all information gathered to a report for either internal verification or for distribution to customers is obviously what GE would like this project to provide. And then finally, designing and building all the hardware to fulfill the various electrical tests defined in the Military Standard 1553 handbook. Arguably the most difficult part of this project was, how do we make a noise generator? The method that the GE currently outsources to is the analog method. This means making a circuit with an input of the voltages you would like to control and a reverse bias diode feeding into the gate of a transistor. The breakdown of this diode just happens to be normally distributed, which means the output of this circuit would be a normally distributed voltage based on your input and the breakdown curve of this diode. This is a massive simplification of the circuit it would take to generate these noise values we were looking for. So we were a little intimidated by it. At the time, we didn't have very much PCB experience, and this seemed like a harder way. Some of the pros were it has been done before, so we know it's possible. Some of the cons were it's little customizability, and we don't see very much in the debugging process. We thought a digital method would be a better way to go. At the time, the company that uses the analog method didn't have access to the digital to analog converters we have today, which means they couldn't output at the rate that would be required to pass these tests. So we thought we would update. The pros of this would be high customizability, which means we can intentionally fail tests if we'd like, or we can decrease the noise to see where the RT actually would pass or fail. The cons is it hasn't been done before, and as we would come to find out, this actually became a lot more difficult than we thought. Before we jumped off the deep end with going straight for the build of this digital noise generator, we would like to prototype. Before even prototyping, we thought it would be a good idea to simulate. So a C programming script was created to simulate a noise generator. The amplitudes of this noise generator were created using two random variable functions in C. These random variable functions are uniformly distributed, but using a clever equation, we can turn them into a normal distribution. When we created this normal distribution, we added one more random uniformly distributed variable, so we could have our uniformly distributed frequency from 1 kHz to 4 MHz, and we could also have varying amplitudes that would be normally distributed. On the left here is the simulated FFT, or fast Fourier transform, of our data. This is 1,000,000 data points, and you can see there's very little ripple in the pass band or the stop band, and we have a steep and controlled roll-off. This is ideal, but we knew in the simulation world, obviously we weren't going to see any environmental noise that might be causing peaks and valleys where we didn't know, but it gave us confidence to move forward. On the right is the analog circuit equivalent that GE currently outsources to. You can see there are some deep valleys in the pass band, which isn't very big deal, but there is also a lot of ripple in the pass band and a lot of ripple in the stop band. This causes higher amplitudes at higher frequencies, which can cause errors. And errors mean more data words need to be sent, and the test takes longer or will fail. So we decided before moving forward, we'd like to have at least a prototype. So a prototype noise generator was created on a DSP, or digital signal processing board. And here you can see varying amplitudes with varying frequencies between them. This gave us confidence to move forward with the build. Then we moved on to the build. We decided with a twin set, an FPGA board that would program whatever amplitudes we need and then output them into the real-life analog world. This output is done by the DAC. The DAC, you can see, plugs into the FPGA board. A useful feature of this FPGA board is you can have two DACs. This means one can output signals that we know will fail the test, and the other can output signals that should pass the test. This gives GE added options in their debugging capabilities. It also comes in a nice enclosure, which is a little bit more noise proof than having just a bare PCB board, and looks nice. The calculations we did to make this normally distributed random noise can be seen here. The aforementioned equation we used in the C script wouldn't work on the FPGA board because of the absence of random variables. C comes with loaded random variables that are uniformly distributed, and the FPGA board did not. This meant we had to make our own LFSRs, 2 to be exact, in order to make these random variable distributions. Also, the natural log isn't supported in the FPGA board that we purchased, so we had to find an equivalent, which looks like this. Then we added what we needed to get the actual amplitudes we needed out of the board, and these were sent to the DAC and then outputted. The following is the results of our noise generator. Here, you can see the output of the digital noise generator, or the one we created. This has an analog filter attached to the end where it's outputting to the bus line, creating this roll-off. Here you can see it's between 4 and 5 megahertz, and we can see that we have a nice steady pass band with very little peaks, a nice sharp roll-off to a lower decibel level, and then a stop band that hardly ever peaks past its normal ripple. Here you can see our noise is indeed normally distributed, and here is the power spectrum density graph where you can see a very uniform distribution. In the second row, you can see our digital noise generator with a digital filter that could be added to further increase the roll-off and drop it further. This would also fairly much kill our stop band where there'd be no ripple at all. This also has the added benefit of letting them control their roll-off. Again, you can see it's normally distributed and uniformly distributed in frequency. Here is the analog equivalent that we have been designing to. You can see in the roll-off some sharp peaks, which is where the power would be located at. This is a problem normally. Also, you can see some ripple in the stop band around 25 megahertz. These can become a problem if you get a high enough peak, which would cause an error and cause the test to go longer. You can also see a normally distributed function and a uniformly distributed frequency. The next hurdle to jump over was the GUI. What does it need to communicate with? An obvious answer would be the operator, and that is indeed an input. He will be controlling the GUI and determining which tests are being run. This GUI will also need to communicate with the Omnibox. This is the bus monitor and bus controller, so it needs to output its data to the GUI to see whether the tests are being failed or passed. Finally, the oscilloscope. The GUI needs to be able to save captures from the oscilloscope to determine when tests are failed, and then give them a waveform to debug. The GUI also needs to output to a report. The report will contain which tests were passed and failed and which tests were skipped. It will also contain a certificate of compliance for signature, the equipment used, and many other things. Using the GUI is very simple. The operator would just, first of all, open up the GUI and select what test he'd like to run. These can either be individual tests, shown here, or a full subset of tests, or even a full run-through. He then enters in all of the relevant information that needs to be included on the report, including the equipment used, and where to save the test folders, as well as customer information, the test personnel, or the operator, the description of the test, and whether or not this will be a formal report for customers or an informal report. Selecting a parent folder is crucial. When you select the icon for selecting a parent folder, this window will pop up. From here, you either make your own folder or you select one that you've already been running tests in. If you select one that you've already run tests in, those tests that have previously been run will be included in the report. This is an easy way to rerun tests without rerunning the full subset of tests and still seeing all of the data outputted to the report. Also, if you'd like new folders, you can perform multiple tests on the same RT and output these different tests to different folders for maybe different customers. Once the tests have been run, after you hit the Run Tests button, you will see a Select Bus icon pop up. Here you will select what bus the tests have been running on, and this will determine where it is saved on the report. If bus A is selected, they will be placed under bus A on the report. The same for bus B, and since some tests require both bus A and B to be selected, we've also added that feature. Here you can see if the test has failed, it will pop up red with test failure in the bottom of the GUI. Also, you can see a progress bar to see how many of the tests you've made it through. If you've selected 4 tests, after the first one is done, the progress bar will be at 25%, and then 50% after the second test, and so on. The GUI then outputs to a report, and this is something of what it would look like. Here we can see the test personnel, when the test was performed, the customer, and many other things. You can also see which equipment was used and a summary of the tests. Finally, you can see a certificate of compliance for a formal report that will be sent to a customer to be signed off on. On the second page, you can see the equipment being used, how many tests were passed, how many tests were failed, and how many tests were skipped. Since we only ran one test and it failed, it only shows up in the failed test section, with nothing showing up in the passed test section, and the rest of the tests showing up in the skipped test section. Since we selected bus A when we outputted, this will be placed under bus A. If bus B was selected the next time, there would be another column attached after this showing the results of bus B. On the third page, we can see a detailed test report. This goes over exactly what the test will do and how it's doing it. It also shows the error and when it occurred. On the final page, we can see the scope captures. Here you can see a scope capture of the failure of the test that was run previously. Another hurdle to jump over was the creation of the hardware to run these tests. This included designing a PCB with a coupling transformer for common mode rejection, the general resistor pad, which is defined in the military standard handbook, and a filtering circuit for the sinusoidal test defined again in the military standard handbook. You'll notice there are strange cutouts through the surface of the PCB. These are for panel-mounted B and C twin-axial and triaxial connectors, where a B and C twin-axial connector will be placed here for the function generator's input. The rest will be triaxial connections for the military standard differential data bus's connection. The inputs are on the left and the outputs are on the right, which means this can be placed right on the bus line in between wherever you'd like. The sinusoidal test will make the messages that are normally square waves into more sinusoidal shaped waves to determine if the RT can still read what the bus controller is sending. The general resistor pad is used for a multitude of electrical tests. On the top is the common mode rejection circuit. Here you'll see a coupling transformer with a turns ratio of 1.41 to 1. This coupling transformer has a connection on the output to the function generator, where the function generator will provide a DC offset, both in the -10 and the +10 directions, to output into the data line. Continuing on with the hardware, an oscilloscope had to be selected that was able to accurately measure a rise time of 20 nanoseconds. Here you can see our calculations for determining what bandwidth is necessary. We decided initially to go with a 100 megahertz bandwidth, which is a fairly common bandwidth for a scope, which would provide a 1.52% measurement error. Since the unavailability of scopes like these was a problem, we were upgraded to a 200 megahertz oscope, which has a 0.38% measurement error. This was obviously an upgrade and helped us out in the end. Some of the challenges along the way were understanding the project. Initially, we didn't know what we were trying to accomplish. This was because we were very unfamiliar with the military standard 1553 handbook and with differential data buses in general. Most of the experience we had as students were in the common mode region with a reference to ground. Unfamiliarity with the field, again, we were very unfamiliar with anything that was military standard. And understanding that we needed to exactly meet the requirements specified in the handbook was a difficult thing for us to achieve. Communicating between new, up-to-date software and older software. This was a huge problem with the GUI and continues to be a problem even with the finished product. The Copilot software that GE uses to run their tests is fairly old now. Trying to communicate with Python version 3.8 scripts and Python version 2.7 scripts has its very, very long lists of difficulties. This meant editing some of the lower level scripts so that we could reliably communicate back and forth without errors causing crashes. This was also seen in a few different areas, especially in communicating with the oscilloscope, where older oscilloscopes don't communicate as well as newer oscilloscopes, so the upgraded oscilloscope we received was definitely a big help. Communicating with the equipment was also a big challenge. We were very unfamiliar with the Astronix Omnibox, which means we didn't really know how to use it for most of the first semester until we sat down with the GE team and they walked us through step by step on what to do. Threading programs to not disrupt time-sensitive scripts. This was another huge issue. With the oscilloscope taking about 10 seconds to capture the oscope, save it to the local disk in the oscope, export that data to the PC, save it to the PC's local disk in the right directory, it took a lot of time. This means we needed to thread the programs so that it wasn't interrupting the tests that were being performed. If it interrupted the tests being performed, it would fail all of the rest of the steps of the test, which meant we'd have to start from square one, and we wouldn't receive the data after the capture we were trying to receive. This also had to be implemented with the GUI, where we couldn't be interrupting the programs running in Copilot with our GUI. This was circumvented by having a 4-thread program, one for the oscilloscope, one for the GUI, one for Copilot, and one for some miscellaneous software we had running in the background. Finally, there were errors everywhere. Copilot had many errors that we could not understand, and seemingly the providers of Copilot did not understand. Emailing between GE and Copilot manufacturers and just trying to figure it out as a team was the only thing that saved us here. Definitely some long hours spent on errors that had a very simple fix. And then choosing the right path, especially with a noise generator. We tried to do an analog circuit first and realized fast that we didn't have the expertise required to make a PCB that complicated. So we went down the digital route, which ended up probably being a lot harder than just finding out how to make a PCB that was that complicated in the first place. Most importantly, what we learned. One was the Military Standard 1553 handbook. It's a 600-page handbook that's open source, and we recommend all of you read it. It's a very interesting read if you want to know more about the military standard world. Read it carefully because there are many typos. The valuable use of resources, whether this be GE's advisors or our professors. We learned very quickly that the use of professors and the GE advisors was going to be crucial in maintaining our progress in this project. The importance of open communication and compromise. We were very fortunate to have a sponsor that was very open to compromise. They knew that some of their lower level scripts were not going to be easily communicated with between newer versions of Python and the versions the scripts were written in. We made some modifications to their lower level scripts, even though we weren't technically supposed to. And since they compromised with us, we were willing to compromise back with them. This was just an important lesson learned in dealing with people in a friendly manner, which is the next thing we learned. Being friendly and easy to work with is probably the most important thing in working in this project. We realized that if we hated each other, we were never going to make any headway. So we determined early, if we had a problem, we'd state it out front, and we'd get it done. This was huge in the final weeks, where we were pulling long hours in getting this project completed. Dedication and scheduling. A testament to Grand Valley's professors is being very, very, very rigorous in making a schedule at the beginning of this project that we needed to maintain. This was huge because we did not realize how big the project was going to be initially. Maintaining our schedule made us think about exactly where we're at and exactly where we need to be. And the dedication to actually be there is a testament to how great the group was working together. And finally, specific and accurate scoping of the project. Again, a testament to Grand Valley's professors. They really made sure we wrote our scoping document detailed. This meant that scope creep, even though it wouldn't have been a problem from our sponsor anyway, was never seen, and we didn't need to worry about the project spiraling out of control from things that other people wanted to add.